Hello, I'm Mrs. Jacobson, and welcome to my math class. Today we're going to cover section 2.2, fitting lines to a data point. Now we're trying to do it linearly. Notice this data is spread all over. When it is spread all over, you can't get a linear fit. Also, they talk a little bit about the correlation. This correlation would be very close to 0. Notice this data fits a straight line. So this would be a exact linear fit, because it all fits on the line. And when it all fits on the line, your R is 1. Or if it's decreasing, -1. So the closer it gets to 1 or -1, the better the fit is. And if it equals 1 or -1, then it's a perfect fit. This last one, you could tell that it's decreasing, and you can get a line pretty close to in between them. So this does have a linear fit, but it's not exact. This R would be close to -0.78, but your R values are all between -1 and 1. Inclusive. If it's 1 or -1, it's an exact linear fit. But if it's close to 1 and -1, then it'll fit a linear line, but not exact. And then if it's all over the place, it's close to 0. So create a linear model. When you're creating a little linear model, you can use Excel, you can use your calculator, you can just graph it to see the line. But my math lab chose the calculator rather than the steps, because the steps, you'd have to find the distance between all the points, and then you have to square them all, and then you add them all up together. So we're going to graph it. Now the Ti84 calculator, up on As You Learn, I put the Ti84 calculator. There's a free 90-day trial. So don't go buy a calculator just for this function. I don't really think we'll be using it for anything else. When you click on it, it'll bring you to this. And then you control click. Oh, come on. Okay. And then you want to pick whichever one of the top two you have. If you have Windows or Macintosh. But whichever one you use, you click on it. And I can't click on it because I already used my 90-day trial in the spring and fall. But it's a really nice online calculator. And you can use it for 90 days. And it looks like this. Well, this is an 83. The 84 is a little bit nicer, but they still do the same. So if you have these data values, move this down so you can see both. To enter these into your calculator, use stats. And then notice the first one says edit. And hit enter. Now, if there were already values in there, you can clear them. You go in stat. See, this one says clear list. You would hit enter. And then whatever lists, see the list here, L1, L2, L3. So I hit second and L1. If I need to clear another list, you hit comma, second and L2, and hit enter, and it will clear the lists. So let's go back in. I hit stat and enter, and then you list them. So list all the X values first. 1, enter, 3, enter, 5, enter, 7, enter, and 9. And then go over to the other side. 4, enter, 7, enter, 10, 13, and 16. And hit enter. To get out, second and quit. Graph it. You want to go under y equals. Let me clear that. And then see the plot on the top? I want to plot the points. So I hit enter to be able to plot it. Notice it's highlighted now. And then go graph. And there's my graph. Now if I want to see more of these points, I can go to my window and maybe make my y value. I need it to go up higher so I can make my y values higher. But did they go? They went up to 16, and I was only going to 10. So I'll go to 20. And there's the points. Notice they're straight in a line. So can it fit a linear equation exactly? Yes. Now to find that linear equation, back to stat, go to test. And then go down till you see linear. Linear regression test. Now you could just do linear line, but this way we'll find our R also. So you hit enter. See L1 and L2, that's your X and your Y. And I put X in L1, and I put the Y values in L2. Leave frequency 1, and then for this test, leave it not equal to. Go to calculate and hit enter. Now notice it says Y equals A, so the A value is 2.5. And then plus B, we have to go down. There's our B. So plus 1.5x. If we go down a little further, it will tell us our R. Notice R is 1. That means it was an exact linear fit. Okay, let's try the next one. So we'll hit clear. I'm going to delete my list first at L1, comma, second L2. And hit enter. So then when I go back in, the list's gone. And I can enter these. 1, enter, 2, enter, 3, enter, 5, 7, 9, and 12. Why did it be the same values? No, it's a little different. And then go over to the Y values. 1, 3, 6. 1, 9, 2, 6. sure I did that right. 361926. Okay. Second and quit. And then we know that plot's highlighted, so we can just graph it. And it looks something like this. Definitely not a perfect fit. So it is not an exact linear fit. We can still find the line. You hit Stat, go over to Test, down until you see linear regression. You hit Enter. And then we go down to Calculate. So y equals the a value, 2.4, depending on how many decimal places they ask for. B is positive, 0.3x. I went to the 10th position. And then if we check the R, notice R 0.36879. It's close to 0. So this is not much of a fit at all. This would be a very bad measurement of this line. So it doesn't fit a linear fit at all because this is weak. Most books say anything 0.5 to 1 or negative 0.5 to negative 1 in that range is strong. But it depends on the book. Yours didn't specify too much yet, so I would say it's up to you. As long as you're showing me your R and explaining it properly, it works. But I would go with at least above 0.5. Any questions? Oh, keep forgetting I'm not in the classroom. Okay, number 23. It's on page 118. There we go. It says, women in the workplace. The number of women in the workplace for selected years from 1930 through 2015 is shown in the following figures. Do the points on the graph and the figure define the number of working women in a discrete or continuous function? Now, discrete means it's countable. 1, 2, 3. Continuous is all the fractions and decimals in between. So when you're talking about time, if it's counting all the minutes, seconds, the whole thing, then it would be continuous. If it's just counting on the hour, then it would be discrete. Now, when we look at this one, they have colored in points. So they connected the lines, but they're only talking about each year because it's points on the graph. So this would be discrete. This one's talking about a graph of the equation. And since it's a graph, notice it's a smooth line. This is continuous. It's not just talking about 1930, there was 10, 1940, there was 20. It is giving you everything in between, all the time in between. So this is continuous. Would the data of the scatter plot be better modeled by a linear function? Definitely not, because if we go to draw a straight line through here, it's just the data's just not going in that type of direction. Notice if we have our point here, this is kind of a cubic function. Next one I want to go over is 26, but before we do 26, we need to understand two definitions. interpolation, and extrapolation. Interpolation is when the data is between the data points given. So if our x values are going from 10 to 60, and we want to use our equation and plug in a value of 40, that's an interpolation because we're using it within our data set. Extrapolation is the opposite of that. If we're going between 10 and 60, anything outside of that value that we want to plug in our equation for x would be an extrapolation. So if we were plugging in 5 or 70, notice they're not between 10 and 60. Those would be extrapolations. Okay, 26. The bottom it says, if 1,000 is invested at 6% simple interest in the value of the future, there you go. So it starts down here. Most of the problems up here though. Value S at the end of each of 5 years are shown in the table that follows. Can a linear function model exactly the points from the table? Explain. Well, in order to explain it, one, you could find the slope from each of these points, and if it's the same, then it can, or we can plug it into our calculator. So if we plug these values into our calculator, clear that. So stat, I need to clear my list, L1 and L2. Then we go stat and edit, and then we're going to plug the x values in. 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1,000, 10, 60, 11, 20, 11, 80, 12, 40, and 1,300. And then graph. Now notice our numbers were so high. And that's why we're not seeing anything. So if we go over to our window, notice the x's go from 0 to 5. So I'm going to go, if you go with 0, you don't see the axis. So I'm going to go -1 to a little larger than 5, maybe 10. So that's my x values. Leave the scale at 1. It always counts by 1, which is good. And then our y value, which is future value or s, goes from 1,000 to 1,300. Now, if you just want that, you can. Or if you want the axis, you could go with -1. But 1,000, I'm going to go at 990 for my low value. And then 1,350. Oops. 1,350. So you want to go a little larger than what your values are. And then I'm going to graph it. There's my line. Notice they all fall in a straight line. Since they are all in a straight line, it will be an exact model. If so, find the linear function. We want to use s for f of t. So we're using s is y and t is x. So you find the equation, stat, test, linear regression, all the way down to calculate. So we have A is first, so 1000 plus 60 B, or 60x. I know the x goes with this one because it says that B is 60 and the B is the slope. Use the model to find the future value of this investment at the end of the 7th year. Okay, so x is years because it's time. So we want to plug 7 in. And they wanted, instead of y's, they wanted s equals 1000 plus 60t. So when plugging things into Alex, or not Alex, but my math lab, make sure you're using the variables that they want. On the test, I would be fine with x and y. So I want to find savings at t, which was the 7th year. I'll just plug that in. Oh, we could also look at R if you want. Oh, I already had entered. R was 1. So the future value would be $1,420. Use the model to find the 7th year. Now, when we find the 7th year, to decide if it's an interpolation or an extrapolation, notice the year values we're given were 0 to 5. Since we were given 0 to 5 and 7 is not in that range, it's an extrapolation. Let's try one more, number 45. The table shows the national expenditure for healthcare in the United States for selected years from 1995 with projections to 2020. Find a linear function that models the data with x equal to the number of years and y equal to expenditures in billions of dollars. Okay, so the first thing we need to do is enter these into the calculator. Clear this. Stat. I'm going to clear my list. And then edit my list. And we're going to enter them. So we enter x first. 1995. 2000. And I'm just going to double check. It's a little hard to see right there. Okay. Then the other values, let me enter them real quick. 1017, 1353, 1981. $13.53, $29.54, $33.08, and $44.87. Okay, round all this time. Now it asks us, to find the linear equation. And x is years, and Y is healthcare expenditures in billions of dollars. So to find the line, well, we won't worry about the graph. Stat, test, linear regression, and hit enter. Go down to calculate and hit enter. So Y equals A, which is a negative 274,954 point. I'm going to go 2 decimal places since we're talking about money. Plus 138.22 x. And to see how strong the relationship is, we'll go to R. R is 0.986, very close to 1. So this is a strong relationship. It's not exact, but it's strong. And so that would be our equation. Find the linear model for healthcare. What does the model predict the expenditure will be in 2018? Oh, okay. Well, that's right. We'll do it both ways. And that's it. 2018. You know, they had wanted us to do something different, and I'll show you that in a minute. So we just plug in 2018 in for X years, and for X. Okay. So when we plug that in, oops, in that way. So when we plug this in, for X, I put the whole year, so we put the whole year. Negative 274,954.25 plus 138 times 2018. So in 2018, it was $3,973 billion. Now, instead of going in years, because this came out strange, that's why they didn't want us to go in years. It actually said, X equal the number of years after 1990. So you want to be careful of that. So if we do after 1990, You go in Stat and Enter. And then I just want to change these. Notice this was 1995, so that would be 5 years after 1990. This is 2000, so it would be 10 years. This would be 15, 20, 25, and 30. So to get it in years, you just subtract the 1990 because it said after 1990. And then Stat, Test, in your regression, go down to Calculate. Notice our numbers are a little bit smaller. Oh, actually a lot smaller. So y equals 97.87 plus 138.22 x. Now they wanted the expenditure in 2018. So if we subtract the 1990, okay, wait, let me show you. Notice the answer is exactly the same. We would plug 28 in because we want the years after 1990. I'm plugging that in. 27.87 minus 1. Plug that in. Comes a little bit off simply because of the rounding. We had all these decimal places here, so this is a little more exact. Oh, this was a plus. That's part of my problem. Three nine 3968.03 billion. So it's close. It's a little bit off because of rounding. These are rounding smaller. But both are correct. Now with my math lab, you'll want to go with this simply because if it asks for you to do it this way, if you're off, then it will take off points. So you would want to do it whatever way they ask. And neither one is correct or wrong. They're both correct. Okay. That's everything in this section.